Hi everyone, my name is Brooke. I'm the machine learning practice lead at Databricks. And we'll get started by talking about what and why are all of you here, with a quick overview as to what deep learning is and why, and a few applications of deep learning. And then a short survey of 3 of the most popular deep learning frameworks, TensorFlow, Keras, and PyTorch. And at the end, we'll talk about different training options, whether you want to train on a single node versus distributed. And then we'll try to save a minute or two for Q&A at the end. So to start off, what is deep learning? I was on Google and trying to find a good definition of deep learning, and I actually couldn't find one that was satisfactory for me. So I came up with this definition. Feel free to critique it, add to it as you please. To me, deep learning is composing representations of data in a hierarchical manner. So this is a very simple feed-forward neural network, just so we're all on the same page. Here, there's an input layer, and the number of units in an input layer corresponds to the number of features you have. The output layer, the number of units in the output layer, is the number of things you want to predict at the end of the day. Some of you will hear the term neurons inside of a neural network. I actually don't like that term.
Agreed.
Neural networks were derived to, the inspiration for neural networks comes from the human brain, but the goal is to not mimic the human brain. And so that's why I like the term unit instead of neuron inside of all of our layers. And you'll actually see that show up in the APIs. They're called hidden units. They're not called hidden neurons. And so just as a little bit of a precursor, deep learning is a subset of machine learning, which is a subset of general artificial intelligence. And there's this paper published by Yann LeCun, Yoshua Bengio, and Geoffrey Hinton, 3 of the most prominent names in deep learning. And to them, deep learning allows a computational model, or deep learning allows computational models that are composed of multiple processing layers to learn representations of data with multiple levels of abstraction. To me, this is why deep learning is a form of hierarchical learning. You have multiple layers of abstract representations of your data, and that's what gives deep learning its power over traditional models such as linear regression or logistic regression. And machine learning is everywhere. Jules, can you think of an application or an industry that has not been disrupted by machine learning or deep learning?
I think it's all over the place. It's in my mind. It's every time I wake up, I think about those terms. So I think it's really permeated my life to the point of fault. So please tell the people why it's the case.
So there's many applications of machine learning, from when you watch movies on Netflix and it comes up with recommendations for you, to when you're walking around the street and there's facial detections of images of humans, classifying who you are, et cetera. But there's a lot of deep learning frameworks. Which one should we pick, Jules?
Something that begins with T?
Something that begins with T. Let us pick TensorFlow. Theano is now deprecated. All right, what else should we pick?
Something that begins with K?
All right, let's go with Keras. All right, one more pick. What should we pick?
I think we have to give credit to Sumit, so we should probably pick PyTorch.
PyTorch. And if any of you had seen our talk back in June in San Francisco, we gave a very similar talk comparing TensorFlow, Keras, and deep learning pipelines. Today we're focusing on TensorFlow, Keras, and PyTorch, and then ways to integrate them with deep learning pipelines all the way at the end. And without further ado, I will let Jules take over, and he will introduce our first deep learning framework, TensorFlow.
Now, most of you are actually wondering, how many of you consider yourself developers here? All of you, raise your hand, because at one point in your life, you're probably writing code or some, and at any time when you're actually developing or learning a new framework, a new platform, a new API, there are a few things you actually have to consider. So what we're going to do is we're going to curate 3 APIs and give you what are some of the developer criteria that you would actually adopt as a developer. 3 things I normally concentrate on, and that's normally community, lots of documentation in APIs. And as an advocate, those are my 3 criteria defined. So with those particular metrics, I'm going to sort of give you a curation of at least TensorFlow. Well, what is TensorFlow? I mean, how many of you heard about TensorFlow? Brilliant. OK, then maybe we should just leave. So it is an open source that was actually developed in 2015. The current version is 1.2 API. They have a very fast, rapid development that's actually going on. 2.0 is coming up very soon, and the emphasis is going to be nothing but ease of use, because over the period of the last few years, they realized that when they introduced TensorFlow, it was very low level, and the adoption was, even though surprisingly very high, but people were a little intimidated by writing TensorFlow code because it presumes a lot of knowledge. It's a declarative toolkit. What I mean by declarative is you actually define your entire model, you statically compile it, and then you execute on the cluster. And it's written in C++, it is fast end. But the interesting history about TensorFlow, from what I've garnered, is that it was built with true proposition in mind. They say we wanted to actually have a very low-level framework where we can actually compute highly intensive mathematical computation using tensors, and tensors are n-dimensional units of data points that you can express as matrix, and you can compute a lot of operations on it. And the other requirement was that they wanted to actually have a framework that if they build any application, they can deploy it in any of the architectures, from CPU to GPU to TPUs and whatever the next version of architecture is going to be. And the interesting part about TensorFlow is this whole notion of data graphs, and I think this is something that actually has come up quite a bit. If you look at Spark, when you express your computation, it's actually expressed as a graph, and then it's actually given to the cluster to compute that. It's a very similar manner. You have actually a graph. You have an excessive graph that has nodes, and nodes can be functional units. They can be activation functions. It could be any mathematical operation you want to perform. And the input is normally tensors of n-dimensional, and output is the same thing. And it is lazily evaluated. What do I mean by lazy evaluation? If you're familiar with Spark, if you actually create a computation, it's lazily evaluated, and when you actually perform an action, that's when the DAG gets materialized and you start executing it in a very similar manner. But most recently, since 1.7, they have introduced what we call eager execution that allows you to do imperative programming. And most of us are very familiar with imperative programming because we think in those particular sequential terms. And from 1.7, if you just enable tf.enable execution, you can actually start executing imperatively rather than doing it dynamically. Some key concepts that I just wanted to introduce before we actually get into some of the nitty details. There's this notion of constants and variables and placeholders and operations. And constants, as the name suggests, is nothing but you define a particular constant and it's going to remain the same. And you give it a particular identifier such as x or y. So then when you look at those variables in the tensor board, you have an ability to identify what those variables are. Placeholder, as the name suggests, is something that's going to hold some kind of a matrix or some kind of a tensor later on, which is going to be the input to your function. And then you have the operations that allow you to operate on tensor. You can do add, you can do multiplication, you can do dot matrix. All these low-level operations that TensorFlow has, you can actually do that. And there are sessions. Sessions are just like Spark session. You create a particular session, and you're going to interact with the session and provide your graph to execute. And then the graphs is the ability, I'm going dark. Thank you. And graphs is where you actually express the computation, and those graphs are executed across your cluster. So what does that mean? How does the code look like? So this is a very simple code of a TensorFlow code. You actually start creating a placeholder. You're going to define your two matrix. Here I have two matrix, 2 by 1, 1 by 2. I'm going to create a metric multiplication. That's my very easy operation. I'm going to create a session, and then I'm going to run that particular session. It reads very much like as if you're writing a new TensorFlow language, doesn't it?
Yes.
It does, yes. So what can you do about it? Well, that's what it is, right? It is a very low-level language. The whole idea is for you to actually sort of get the control over a very low-level language. And that's what you do. You execute, and you get the output. To give you another example of why it is such a low-level language, because we as developers, and most of you who raised your hand, in fact, all of you who raised your hands, are control freaks. You really want to control how you do things, and TensorFlow allows you to do that. And here's a very small example of MNIST, which I don't expect you to read all that code, but I just want to give you an idea of how low level we actually get to the TensorFlow. You actually create your input variable. TensorFlow has those libraries that allow you to take input, process it in a manner that you can actually understand. You create your placeholders. You create your model that you actually want to predict on. Now you actually have to define your loss functions and your optimizer that you're going to use. You create your session, you evaluate your model, and you actually go on. But you can actually see over here that it presumes you know a lot concepts about machine learning, you know a lot about data science, you know exactly what optimizer to use, what gradient descent algorithm you should use to optimize your model, and so on and so forth. But for those of you actually new, it gets a bit too hairy, and somehow you be a bit less conducive for you to actually learn. But what they did eventually over time is that this is your programming stack of TensorFlow. You can actually come in from a very high level, or you can come in from a very low level. And the reason why you want to do that is because if you feel comfortable at a high level, you can actually use what they call canned estimators. So they have the ability to use those estimators that actually have all the parameters tuned for you, so you can actually use it. So that way you don't have to write your own. The oldest second level, mid-level API is called layers and data sets that allow you to ingest data, define the metrics that you actually want to observe when you actually do your models. And then you can write in any of these languages, right? You can write in Python, you can write in C++ and Java. Recently actually announced the ability to do it on Swift and JavaScript as well. Anybody who's doing JavaScript over here? Silence is a form of complicity.
Oh, one hand went up over there.
Very don't be shy. You can actually write TensorFlow in JavaScript, and it has the ability to actually deploy on any of these particular frameworks. So that's one of the most attractive part of the feature. But I think the other part, the most attractive part, is the ability to actually take hold of the community. There's a large community of people, right? There's a large community that you can actually learn from. There are lots of code examples. There's lots of tutorials. There's lots of people in the community. How many of you over here, at one point in midnight, you've written some particular code, you got an error exception, and you've literally taken the error exception, cut and paste, and put it on Stack Overflow? You sure? Yes, you have done that. And some guy, some gal will actually respond that. Not out of the fact that she wants out of vanity, but he or she really wants to help you. And that's the reason why community is actually important. TensorFlow has that large community. But then you might ask, what are some of the other tools available with TensorFlow? Now, those of you who actually are involved in writing multi-threaded program, it's one thing to debug a program on a single CPU where you don't have all this complexity of rest conditions. It's a completely different ballgame when you're actually doing multi-thread programming on multiple cores which are across the network. How do you actually debug that particular program? How do you look at your graph? How do you inspect your graph to see what's going on? And TensorBoard is one way you can actually do that after the fact, where you have executed your model and you want to find out what's going on. The other thing that once you have actually done that, you can actually now deploy those models through their TensorFlow model, TFX, which is ability to version a particular model and then deploy it on the architecture on which TensorFlow supports. So what? Right? Brooke always gives me a hard time. He says, you told me all the good things about it, so what? What does that mean to you? What does that mean to me as a developer? Well, there are a few things I have to admit. There's a steep learning curve. No question about that. I won't deny it. It took me a while. But it's very powerful, right? Powerful in the sense it gives you control. Because of the low-level API, it has the ability for you to tell it how to do something. If you compare that to Spark, data frames give you the ability to how to do something or what to do something. Gives you the ability to how to do it. It presumes you're no expert in machine learning, but there's nothing wrong in that, right? Machine learning is now becoming a very ubiquitous skill. Pretty soon it's going to be as imperative as you knowing algebra. So learn it. And there are high-level estimators that allow you to come in from high level or you come in from the low level, whatever your comfort level is. And the 2.0 actually has the ease of use and eager execution because people realized that they actually wanted to reach to the larger community who don't get intimidated by the low-level API of TensorFlow. And Keras, obviously, is the saving grace. And even the advocates actually say that if you want to learn TensorFlow, start with Keras. And to tell you all about Keras is my esteemed colleague here, Brooke.
All right, thank you, Jules. All right, so Jules just presented on TensorFlow, which is a rather low-level API. They do have some higher-level APIs with the canned estimators. I actually prefer using Keras. It is an open-source Python library for deep learning. It also has some bindings in some other languages, notably R. And it was released by Francois Chalais of Google. And so Keras is a high-level wrapper that supports 3 different backends currently: Theano, CNTK, and TensorFlow. And so one of the nice things about using Keras is that you don't have library lock-in. If you use Keras, you don't have to stick to TensorFlow. Later on down the road, your company might say, we want to use CNTK. You can easily switch between the two. So very easy to use, great for building neural networks from CNNs to RNNs and LSTMs, very fast for experimentation. So that piece of code that Jules had displayed up here for MNIST, that could be written about 5 to 10 lines of code using Keras. So this is the Keras programming stack, Python API, multiple backends. And then depending on the backend you use, there are different things available for you. For example, you can use TensorFlow, and you can use a Keras callback. So you can use TensorBoard, and you can use it across any of these different devices.
And you can run it on Raspberry Pi.
Yes.
There was a pickle
was
person in
TensorFlow.
Japan. That was TensorFlow. But you can actually write it in Keras as well. Yeah.
Exactly. Yeah, there was a cucumber farmer in Japan who had built a TensorFlow model to classify different types of pickles for him automatically.
Anybody has Raspberry Pi at home? Okay, your task tonight is to download TensorFlow applications that's actually built for Raspberry Pi and you'll see the lights going crazy.
And build the cucumber.
And build the, so there are applications available you can actually download and actually run it. I recommend that if you want some psychedelic lightning in the room, then TensorFlow and Raspberry Pi will do that to you.
All right, so why do you want to use Keras? Oh, there we go. It all went at once. OK. So here we can take a look at the interest worldwide of searches for Keras, and it actually beats TensorFlow. Even though it supports TensorFlow as a backend, lots of people like using Keras as a good way to get into neural networks. The analogy here I like to give is if you first start off learning a programming language, you don't want to start off with C and C++. That's what I did in college. Now colleges are switching to higher level languages like Python and then going back to C++. And so it's kind of the same analogy between Keras and TensorFlow. Keras is the higher level API. It's much easier to pick up. But when you want lower level control, that's when you can go back to TensorFlow.
How would you compare that to the Spark APIs? Is it something similar to like RDD and data frames?
Exactly. You get more control with RDDs, but then you can get, in the case of RDD versus data frame, there's additional optimizations, but the API is much cleaner using the data frame API. So yeah, a very broad community, has over 250,000 users, supports multiple backends, and it has two different types of models you can build, sequential and functional. With the functional API, you can have multiple different sources of inputs to your neural network, and in addition, multiple different outputs. So you could build a model that will try to classify an image and generate text at the same time. So two different outputs jointly trained on the same data source. And you can also have layers as input to other layers down the road, so different residual connections. And you can see how clean the code is here. It's quite easy to understand. Here, I'm going to build a sequential model, and I'm going to add a layer to it. My input dimension is going to be 784, so that would be the number of pixels I have in that image. And my hidden layer I'm going to create is now going to have 32 units, and it's going to have rel use the activation function. And then I keep adding layers on top of that. I can even put the activation function inside of the layer that I'm adding. All right, so when you work with Keras, there are 5 main steps that you commonly take. Precursor to any step is you load in your data set. And then you define your network. So you define the architecture you want to use, how many hidden layers, how many units per hidden layer, your activation function. And then you compile the network. You specify which optimizer you want to use, your learning rate, the loss you care about, any metrics you want to display. And then you fit your network to your training data set. You specify the number of epochs you want it to run for, the batch size that you want to process at a time. You evaluate it on your test set or on your validation data set. And then you apply it to make predictions on new data points coming in. So you can see this API is quite clean, very easy to use.
Compared to the TensorFlow we actually saw. Yeah. But there's something else I saw. I think there is a rhythm here. You know, there's a pattern. You define your variables. You input your data, you define your loss function, then you build your network, you do train the model, and then evaluate. And this seems to be consistent. We saw that in the TensorFlow. We're seeing it in MNIST. Are we going to see in the other framework?
We shall. All right, so that was just an example of Keras code. And here I want to show you an example of code from TensorFlow, Keras, and PyTorch side by side. So you'll notice that this is very squished TensorFlow code. TensorFlow, you actually have to write quite a bit of boilerplate code. You have to worry about, am I in training mode? Am I in eval mode? Am I in predict mode? So depending on the mode I'm in, I might want to print out different metrics. So that's not even displayed here. So this is TensorFlow over on the left-hand side. In the middle is Keras. I love Keras. That is why I have started as my favorite of these two so far. You simply just add layers as you go along. And then over here we have PyTorch. And notably, the syntax is quite different from these two, but PyTorch syntax is actually much more similar to Python syntax.
In a way it is, and it's a good cross between TensorFlow and Keras, and somewhere in between. And I guess it actually makes sense when we do talk about PyTorch, but Sumi talks about it, so I think we can just end the class.
we'll do a quick overview of PyTorch, or actually, Jules will do a quick overview of PyTorch.
Okay. Well, you heard about from the creator from PyTorch today, Sumit, and he sort of gave you an overview. So some of the slides might be actually repeated, but conceptually, I think the idea is same. It's an open source community. Today, as this morning, the developer released 1.0 that has a lot of new features that they actually added, including all the other ecosystem Python packages included. One of the attractive things about their TensorFlow package is this notion called tensor computation. They have their own library called Torch Tensor, which is equivalent to NumPy, and it allows you to go back and forth between CPU and GPU, and it's a very efficient way to do that. So if you're actually using their package called tensors, you get that particular benefit. There is another added function that's a very dynamic language. So your graphs are actually executed dynamically, and it's based on the fact that you can actually do auto-derivative of all your variables. So any variables that you actually have, you can create the gradient automatically, and it will compute its gradient with respect to the graph it's associated with. So it's very simple. It's a very imperative toolkit. And what I mean by imperative toolkit is unlike TensorFlow, you actually had to define your entire network, and you had to compile it, and you had to submit that for execution. Whereas the imperative nature is something very similar to what you and I are very familiar with, whereby we do the imperative way of programming. And as you create your node, it gets actually executed dynamically right there. And because of this auto-gradient, automat derivative function, you compute your gradients with respect to your weights right there and there, rather than waiting for the entire graph. So that's actually one of the attractive features of that. It's very imperative. It feels like you're writing Python code, which is different from TensorFlow, where it feels like you actually have to learn a new methodology or a new way of thinking of how you actually write that. And this makes it a lot easier for people who are Python programmers to make the transition, because it's just like writing Python code. You can just get in debug and start debugging it very easily. You don't need a special debugger for that. Like all the two languages or all the two framework, it has a stack as well. And there are four very important high-level modules or high-level components that make things a lot easier for people who are actually getting started. One is the ability to actually do the auto-differentiation engine, the lens itself that has models, that has a forward function that allows you to do backward propagation rather easily, because of this notion called auto-grade differentiation engine that automatically computes all the derivatives with respect to all the other weights associated with that. There is this very high level or very efficient NumPy alternative called torch.tensors that allow you to move back and forth between NumPy as well as between torch tensor. And you don't have to pay as much as cost, because what they do is they actually keep a point zero copy. They actually have it in the memory. So when you're going from NumPy array, they both have pointers, and it just copies right away. So you actually don't have to worry about copying the entire stack. So that's very efficient. They also have a large number of optimizers that actually come straight out of the box with all the appropriate parameters for you to actually use that. And like any other framework, if you're going to be reading a lot of input, you need utilities for it to normalize the data, to put it in a format that it can actually understand. And that's what it is. You can deploy it on any of the model. And why PyTorch is very imperative. It's easy to debug, quick wrap-up time. There's loads of community, and it's integrated with TensorFlow as well. TensorBoard as well. So any models that you actually create using using PyTorch, you can look at what the models looks like in PyTorch as well. Very same concept. You actually have the ability to define variables with the ability to say, this is going to be my auto gradients, or compute my gradients as you go along. Very easy. You define that, and then you can use the backward propagation to compute your gradient and do that. Tensors, very easy. Again, you define a particular tensor, very intuitive way. I know exactly what I'm going to do. I'm going to multiply, I'm going to add, and I'm going to convert my NP array into the tensor. And the operations are no different, very intuitive, just like you're writing Python code. If I do x plus y over here, I'm actually doing matrix addition. If I wanted to have this operated on CUDA, you do that by checking to see if CUDA is available. And any operation you perform thereafter is going to be done on CUDA. And so that's actually very easy to read. It's very Pythonic, as my esteemed friend over here likes to call it. And there is a rhythm, right? There is a rhythm to Python, just like we saw rhythm in Keras, we saw rhythm in TensorFlow. You design a model using your auto variable, you define your variables, you construct what your loss functions are, what your optimizer are, and then you actually have a training loop, and then you actually evaluate. And just to give you sort of a quick example of what this looks like, again, step one, I'm defining my particular variable. This is a very small logistic regression toy example, but I just wanted to illustrate how easy it is for you to actually just do those things. And all it does is, given a particular hours, if I'm going to study for that many hours, am I going to pass my test? And then we actually have the labels. We create the forward function. We wrap the forward function around sigmoid, so we actually get the probability between 0 and 1. We define our binary cross-entropy loss. We define our optimizer, and then we get into the loop over here, and we just keep on training the model. And once we are done, we evaluate. Very simple, very easy, very intuitive. There's a flow, there's a rhythm. And if you come from a Python background, you don't see as if you're actually learning an entire new framework. You're doing as if you're writing in Python. But the question is, how do you actually train these particular models? You got 3 frameworks. What choice do I have? Do I train it on a single node? And that's what Brooke is going to talk about. What are some of the training options available for us?
Thank you, Jules. All right, so to start off, the simplest training option is on single node, single GPU. Thank you. Single node, single GPU. But sometimes you have so much data, your model is so big, that is no longer feasible. So then the next thing people do, single node, multi-GPU. While that works, what happens if you need to worry about distributed training or distributed inference? So the next logical step is you train on a single node, you have multiple GPUs, but you'll apply in parallel. And when you do distributed inference, sometimes people switch to cheaper architectures. They'll do single node training with the GPU instance, but then they'll do distributed inference with CPU. But then what if your model and data are so massive they can't fit on a single machine? That's when we have to take a look at distributed training. And so the distributed training I'm going to present to all of you today is called Horovod. It is an open source framework released by Uber. And it simplifies distributed neural network training. And part of the reason why I'm introducing this framework in particular is because it supports TensorFlow, Keras, and PyTorch. So no matter which framework you had picked earlier, based off of the conversation Jules and I had, you can use it with Horovod. So to start off, let's motivate Horovod. So this is the classical parameter server technique. Here, if you have multiple workers and you have a single parameter server, your parameter server is now the bottleneck. Imagine if you had 200 workers. All of them have to communicate with the parameter server, get the updated weights for your model, pull them, update them, push back. And so this is our bottleneck. So an alternative to this is to have multiple parameter servers, each of them averaging some portion of the gradients. But then you also have this complication because you have lots of communication, and you have to write separate code for your parameter servers and your workers that are actually doing the work. So Horovod uses this technique called all reduce. And so that's where it derives its name from. Horovod is a Russian folk dance where everybody goes around in a circle. That's the key idea behind Horovod here. Here you have, in this case, 3 workers. Each worker has a subset of the data but has a full copy of the model. And they compute their gradient contribution, and then they update their neighbor. Their neighbor does the same thing, updates their neighbor. And so it goes around in this ring fashion. And so it uses this technique called ring all reduce. But to me, one of the most beautiful things about Horovod is that you write your code per usual. So this is just vanilla Keras code. The only piece of code I have to change to make this run in a distributed setting is to wrap my Keras optimizer inside of the Horovod distributed optimizer. And I can also scale the optimizer learning rate by the number of workers I have available. And so you can build your distributed model using Horovod, and then you can always apply in parallel, and you can use libraries such as deep learning pipelines. We have an author of deep learning pipelines in the room if any of you have questions afterwards. All right, so Jules, which one should we pick? TensorFlow, Keras, or PyTorch?
Well, we can ask the crowd, or we can give them the reality.
The reality is that it actually depends on which region of the world you're from. So earlier we had showed worldwide there's greater interest for Keras over TensorFlow. But if you come from the UK, more people from the UK are actually searching for TensorFlow over Keras. And if you come from the States, more people from the States are also searching for TensorFlow over Keras. So you can infer which countries are more likely to be using Keras instead of TensorFlow.
But given that the advocates of TensorFlow are now pushing more Keras because it's a lot easier if we do that. After all the Keras code does get compiled in TensorFlow, and then So it gives them the ability to actually reach a larger community. So I would definitely start with Keras if I was beginning to learn deep learning in this case.
Exactly. And in addition, Keras is now integrated as part of TensorFlow. So instead of specifying your backend when you're using Keras, you could also say from TensorFlow import Keras. All right, so when do you want to use TensorFlow, Keras, or PyTorch? When do you want to use TensorFlow, Jules?
If you like control, I would definitely go for low level. If you feel comfortable about your knowledge in machine learning and you know exactly how you're doing it and what you want to do something, then you would actually go there. It gives you the ability to do model serving. And if you want to be a polyglot where you can actually write your models in any languages you actually want, that's the way to go.
All right. I like using Keras if you want to be able to support multiple backends, so you don't have that problem, hey, Theano's now deprecated. No problem. I can keep running my Keras code as usual, but use TensorFlow as my backend.
And if you love Python, it's a very Pythonic, it's a very imperative way of programming something, and rapid experimentation. So if you really want to come up to speed, PyTorch is definitely something I would highly, highly, highly recommend.
And if I were to just do a language analogy here, to me, TensorFlow is C, Keras is Python, PyTorch is C++. It's the in-between TensorFlow and Keras, and it supports object-oriented programming. All right, if any of you are interested, Databricks Runtime for Machine Learning comes with all of these libraries pre-installed, as well as GPU support on Azure and AWS. And if you want any follow-up resources, there are two things I want to make a great call out to. One is Francois Chalet's book, Deep Learning with Python. It's a fantastic intro to Keras, as well as Fast.ai. Sumit had talked about this earlier today. It's a class, V1 was based on Keras. V2 is using PyTorch. They had actually switched to PyTorch because they wanted to do some customizations to the library.
And I think we are out of time, but we're going to hang around here since it's coffee break. I don't want you to hold you back from coffee, but we'll be around if you have any questions. But thanks a lot for coming over, Talk, and I hope this was just a sort of a high-level curation of those who are getting started in those deep learning framework, and which one you want to start is a good way of giving you sort of an insight into where you get actually started. But go for it, get enlightened. Keras and PyTorch.
OK, thanks, Brooke and Jules, for the talk. We actually have time for 2 questions. Do we want to?
Yes. 1 sec, the mic's.
We need to get the mic.
As from a data engineering perspective, does it make a difference which of these the data scientists use in terms of deployment to production?
That is an excellent question, and that's actually something I always consider first whenever I build models for customers. So something I'll consider if they need to deploy the REST endpoint at the end of the day, like I wouldn't use SparkML for that. In terms of model deployment for these 3 different frameworks, you can always convert a Keras model to a TensorFlow model, and TensorFlow has multiple serving options. I haven't used PyTorch for any deployment, so I can't speak to that one, but I know TensorFlow and Keras are very, very easy to deploy.
And then all these frameworks are actually integrated with MLflow. So if you are one of the data scientists want to use MLflow models, then you can actually use that. But I mean, language is an important part. It becomes a rather religious issue. Like editor, am I going to use VI? Am I going to use Emacs? Is it C++ or Java? But I think organizationally, some things just stand out. And Python seems to be the winning language today in terms of the data science. We have time for one more question.
One last question.
Can you see so if you're using Keras and you're compiling to TensorFlow, can you actually see the graph that's being created in TensorFlow from the Keras model?
Yeah, so if you want to be able to visualize the graph that's being generated, you can use something called a Keras callback. And so a Keras callback, after every epoch, you can do a call out, and so it can trigger TensorBoard, and so it can show you the updates on TensorBoard, like your loss over time. It can also show you the graph that it's generated for you. So Keras integrates very well with TensorBoard.
OK, thanks, Jules and Brooke.
Thank you.
Thank you.